Good afternoon, good morning, shalom to all. Welcome to the Advanced Sensing Payload for UAV and UGV webinar. My name is Nofar Sharan Reicher. I'm the Autonomous Systems Society Manager. The Israeli Society for Autonomous Systems is a home for tens of thousands of engineers, managers, and administrators, physicians, optical systems engineers engaged in the various branches of unmanned systems. The Society creates space for training and professional upscaling. The Society conducts conferences, seminars, workshops, and courses, as well as collaboration with universities around the world. Participation in the Society enables professional and continuous contact with experts, engineers, and the world of academia and industry, including relations with leading international organizations such as AUVSI. The Society is a branch of AUVSI and conducts joint expositions and support for companies in the various frameworks. The Society established a holistic approach for UA regulation and is collaborating with the Prime Minister's Office to establish acceptable regulations for autonomous systems. We invite you to sign up to follow the activities we hold, which were published in our monthly newsletter. Per your request, the newsletter will be delivered to your mail. I'm honored to introduce Ronnie Gordana. Ronnie Gordana is the chairman of Propulsion Systems branch at AEAI, and from last week is also a co-director of Mechanical Aviation and Space Society at AEAI. Ronnie Gordana, a Master of Science, aeronautical engineer, and have 2 executive MBA. More than 25 years at R&D, 20 years as Director of Defense R&D at Ministry of Defense. Last position was Defense Attaché for R&D in India. Currently is working with startups and companies on empowering their technology strategies, spin-offs and technological added value. Mentor in several accelerators in Israel. Ronnie, the stage is yours.
Hi, thank you, Nofar. Good afternoon, all. Welcome to Dr. Nir Karasikov lecture. It will be today on advanced piezo-based sensing payload for UAVs and UGV. Something about Dr. Nir Karasikov. He joined Nanomotion in '97, more than 23 years ago, as a vice president for R&D. After that, he was appointed as a general manager, CEO of the company, and eventually became a CTO. Since joining the company, he leads the company activity in precision motor, turning the company into a major player in the semicon and defense motion market. Prior to his joining Nanomotion, Dr. Karasikov was involved many years in various high-tech industries, leading the development of infrared system, electro-optic system, laser-based metrology system, security system, image analysis system, and precision mechanical system for microscopy. Dr. Karasikov has the broad experience in developing and introducing new pioneering technologies into the market and in collaboration with major worldwide corporates. Since acquiring his doctorate in material science and solid state physics from the Technion, Dr. Karasikov has also authored over 60 articles in his field and involved in many tens of patents, over tens of applications in electro-optics, inspection, and piezo-electric related fields. Something about, a little bit about the company. The company Nanomotion now is a part of a big concern, Hong Kongian concern. Is a company that have a multidisciplinary capabilities, dealing with piezo-electric propulsion in the area of semicon, medical, and defense. In that field, she is leading in the world. The company, due to the capabilities of the company and to the wide knowledge and to the interdisciplinary knowledge, she became, let's say, leading in that part in the world. This lecture will deal with the advanced piezo-based sensing payload for UAV and UGV, and the unique added value that this technology can give to the payload. We will have some case studies, and I hope that by the end of the lecture, you will first of all know the technology much better. You will be aware of the technology, and of course, after it, you also will start to dream about some using this building block technology that Nanomotion have in order to enable a new area of uses for that technology. I hope you will enjoy the lecture, and feel free to ask questions through the Zoom, and we hope to answer most of them at the end of the lecture. Thank you very much. Nir, the stage is yours. Good luck.
Thank you, Ronnie. Thank you, Nofar. I appreciate the excellent organization of this opportunity, and we are excited to present in this forum. Let me share. Okay, can everyone see? Can you see? Nofar, can you see?
Yes, everything is clear.
So as Ronnie said, that the title, actually we added the piezo-based because really this is what we are doing. And when Ronnie gave my history, he mentioned electro-optics, infrared, precision mechanics, etc. And actually the payload really benefit from all this. It's a combination of a precision electro-optic mechanical system. Let me just cover what we want to present. So a little background about Nanomotion. I know that there are quite a few overseas attendees here. What is the piezo effect and its advantages? Design consideration for payload. Use of UAVs. For UAVs, you will see issues like stabilization, mosaic, analytics, super resolution, and use in AGVs, which is autonomous ground vehicle, and a summary. So a few words about the company. The company was founded in '92. We became part of Johnson Electric, the large Hong Kongian concern, in 2005. We are 110 people, 35% of them are in R&D. We have over 200,000 motors in the field, over 100 precision axis or motion stages in the field. And in the past, we did 3 million motors for consumer electronics for autofocus of Samsung cellular phones. This picture is actually our old building. We moved in the same street, just across the street, to a new building, larger, more modern. And I apologize for leaving this picture. I hope that you will come and visit us, and then you will see the new beautiful building. So the company, I will move this because it's blocking. Yeah. So Johnson Electric is a $3.4 billion company, 38,000 employees. A number that always impresses me is that they make 2.5 million motors a day. So I also like to say that together with Johnson Electric, we do over 2.5 million motors a day. The areas they cover are white goods, a lot of automotive, power tools, really a very, very highly organized, deep technology company. And this is our niche in this big pie. Nanomotion, as Ronnie said, everything we do is piezo-electric. So we are involved mainly in 3 markets. Traditionally, the semicon market. Attendees from Israel know that, I guess, know that we are involved with all the big players in Israel, Applied, Nova, Bruker, as in relations, including joint consortia. Medical industry, where our major benefit is the fact that the motors can be non-magnetic and therefore can be operational in MRI. And in recent fields, recent 5-6 years, a lot of activity in the defense and commercial electronics, where a payload is the top of this in the value proposition the company is doing. So from product perspective, we go by layers. The lowest layer is components. It can be motor, drivers. It can be building blocks. Ronnie mentioned building blocks. For example, this shutter is being sold like 20,000 pieces per year for infrared cameras. And on the top, more comprehensive motion solutions. And I will show a few just to give you a flavor. So this crazy small piezoelectric motor is in several unbelievable applications, and you will see it in the next slide. So I put here 3 things. One, space. I gave a few months ago a lecture about space consideration. We have a few tens of these units working in space in LEO. LEO is low Earth orbit. But especially I wanted to draw the attention of the forum to these 2 pictures. Here is a rotary stage with a sub-microradian resolution, and this is a linear stage with a sub-nanometer resolution. So nanometer resolution is important for semicon, etc. The microradian resolution and the capability to reach this level will be reflected also on the lecture of today. It's an outstanding benefit for a gimbal, whether it is a gimbal payload with a camera or a payload with a laser. Let's just think about a laser with a divergence of 100 microradians. You need to align it to better than 10% of that. So let's say 10 microradians, we have the capability to do it. So the gimbals, the payloads, excuse me for switching the word, I should say payload because it's the complete solution. Gimbal is just the mechanical part of it. But the gimbals or the payload stems from this capability. I just want to show off on this stage and show something that I don't think anyone else in the world can do. By the way, just to give a dimension, this here is 800 millimeter, and the moving mass on this stage is 30 kilograms. So here what you see is a record of the position, the encoder resolution here, the blue is the record, plus minus 2 nanometer stability. But look at this, the time duration is 3 hours, 10,000 seconds, and the position did not drift 1 nanometer. Without mentioning names of alternative solutions, to achieve stability of 1 nanometer for 30 milliseconds is a challenge. We are doing it for 3 hours. And of course, in the state of the art of semiconductor, this is highly reflected and appreciated. Now about this bizarre animal, which is called piezo. So piezo is the effect of coupling between mechanical deformation and electric field. This effect was revealed by two French brothers, Pierre and Jacques Curie, in 1882. So whenever I see paintings of the Impressionisms, I think that in parallel to the superior art, France was also very much leading in science, and they understood and characterized the piezo effect. So the piezo material itself is a ceramic material which has what is called spontaneous polarization. A normal position, the more stable energy state, is that the ceramic has a spontaneous polarization. Here you can see that the spontaneous polarization indicated by these arrows as an average, macroscopic average is 0. And this is logical because of more stable state. By polarizing it, one can align all the dipoles or all the polarization in a preferred direction in space, and then you get macroscopic polarization. This macroscopic polarization helps in coupling between electric field and mechanical deformation, as shown here. So this is the unit cube structure of the piezo material. In this case, the piezo material is a material when there is a coupling between mechanical deformation and electric field, and PZT is just one type of material. PZT stands from lead, zirconate, titanate. And there are two positions here. You can see where this more stable at room temperature situation is that the O2 is shifted from the center and creates in the unit cell of this ceramic a polarization. Now what happens is when we apply voltage, we have a dipole here. We can extend or shrink this dipole, and by extending or shrinking the dipole, we elongate or shorten the size of the crystal. So this is the coupling between electric field and mechanical deformation. It stems from the spontaneous polarization, and it has to do with the structure of the unit cell of the crystal or the ceramic, where the equilibrium, there is a dipole in it. So this was more in physical term. In more illustrative form, you can see here the direct effect is that you put the pressure on a piezo material and you get voltage. We all know it from lighters, igniters. I know at least one of the attendees is a heavy cigar smoker, and he can light a cigar with it. But we don't use this effect. In our motor, we use the reverse effect, or actually I should say the inverse effect. The inverse effect is that you apply electric field and you create mechanical motion. Just to show you, this is a slide that we put many years ago, that this crazy piezo is very common in actuation. Everyone has a reverse sensor. It's a piezo. So there are many applications of piezo. Our expertise as Nanomotion is in the actuator and especially ultrasonic motors. And the next slide will show how our motor is built. So first of all, let's start with this movie. Based on this, by the way, I think we should try and sell in United Arab Emirates, because the element, the piezo element, is doing belly dancing. So what you see here is a piezo element, which is rectangular. We have many tens of patents on this technology. The element has on it these gray electrodes. The gray electrodes are operated like this. Watch what I'm doing. If we operate one diagonal or the other diagonal, we create a miniature elliptical motion here that is doing a rowing effect and moving the application, whether it is a lens or whatever, or a gimbal, to the left or to the right. There is a lot of knowledge on the structure here, and I invite Tuvia, which is on the line. Tuvia Teiblum is our sales and marketing manager in Israel, and he will be very happy to circulate material as needed or elaborate more. I don't want to go into the design, into any details because I'm limited in time, but basically a very robust solution, very different and very superior from any piezo motor available in the world. And indeed, in piezo motion motors, we are the leaders. And this, by the way, forced us to develop deep knowledge in the physics, in the mechanics, in the electronics, in the control algorithm, etc. And indeed, the R&D team supports all this application. By the way, we published a paper about this L1B2 ultrasonic motor, and whoever wants it can get this paper. So this is how our motor works. I hope it's clear. Advantages of the technology. High power density, which means, for example, in a small motor, we have 10 times more power density compared to an electromagnetic motor. Even though the name of the company is Nanomotion, we can do unlimited travel. The nano goes for the resolution rather than for the travel. Direct drive meaning there is no gear, no backlash, and every point like this, think about its advantages in a gimbal where you want to move with a very high accuracy and very high speed. Compact dimension, high resolution, high dynamic range. The motor can go from 1 micron per second to 0.5 meter per second, very fast response time. Built-in brake, which means if I go back to this, you have a back spring. So even if the motor is not energized, there is a contact here, and the application is held by static friction. I know that some payloads which use electromagnetic motors, you need to fly to the target. The target can be half an hour away. You need to fly with the servo on, which means consuming power, because otherwise it will damage the gimbal. In our case, you don't need to do that. The payload holds itself by static forces. Very important. And another important thing is the built-in clutch. Miniature motors, electromagnetic motors with the gear, are very vulnerable to shock because the shock can break a teeth in the gear. In our case, the contact, if I go here again, is by friction. And if somebody will override the motor and push back, it will go back, nothing will happen. And these all are extreme advantages, and that's why I think the defense community on defense optronics are so receptive to our technology, because it can operate under conditions that miniature conventional motors cannot work. No intrinsic magnetic field, which could be an advantage, and UHV compatibility. UHV is ultra high vacuum compatibility, but I don't think it's relevant for this forum. So why piezo in gimbals? Swap size, weight, and power. Small size, small weight, and low power. Very important. Zero backlash. in vibration all the time, the gimbal can change position. So basically, if there is a backlash, you don't have a good control. Very high bandwidth, I will show some body plots, very high torque, which means high acceleration, and you will see what we were able to do with this high acceleration. Friction, of course, people that are familiar with gimbals, are the default or the prevailing approach, let's use zero friction. In zero friction, basically, no matter the vibration, the inertia will keep the line of sight to the right direction and will therefore stabilize. And what they use is they use motors to overcome the residual friction of a non-ideal bearing. We actually work by friction. And we were able to develop algorithms, a technique to solve it, and on the contrary, to take advantage of the friction of the gimbal and achieve outstanding performance, as I hope I will be able to show you in this presentation. So we have three sizes of gimbal. These gimbals were for the more for the defense market. So starting from the large one is 1.2 kilo. And by the way, I think I mentioned the advantages here on this slide. I think that I want the forum to put a number, like if the mechanical power is up to a few watts, is good to use our piezo-electric motors. If this is something which needs tens of watts, there is no merit in using it. So from size perspective, this criteria of a few watts is saying that this is typically, I would say, the maximum size of gimbal that we can do. 1.2 kilogram, 114 millimeter diameter. And you can see here the name Micropop because this was in collaboration with the Israel aerospace industry. And two other gimbals, including a very small one, I think extremely small, which is facilitated by the size, weight, and power advantage of our payload motors. And recently, we are putting a lot of effort on a commercial market. We developed a product which is called the Velocs. This one is a thermal Velocs. It is a non-ITAR to the people that are non-US citizens and suffer from the fact that some components require ITAR. This is no ITAR. We can sell it everywhere we want. And it's seamless. It has seamless integration to a DJI drone. DJI is the largest drone manufacturer in the world, holding over 85% of the market. And we are aiming for this market niche. So this is the configuration of this is the DJI drone. This is our payload on it. And it clicks into the gimbal, and we have our software here to do unique features, which I'm going to show you. So our major efforts now are on the commercial market, and we are very interested to pursue this thermal Velocs, which has one camera, or the dual Velocs, which has IR plus electro-optic camera on the same payload. The motors that facilitate these capabilities are two of our standard motors. We have sold hundreds of thousands of these motors. So there is a motor called the Edge. This is, by the way, a standard nail, not something exaggerated. So the motor is really small. So we have a motor, the edge, which weighs 0.55 gram and gives a force of 0.4 Newton. We have a bigger one, which weighs 4 times more and gives 4 times more power. These are the building blocks for our defense electronics in general and the payload segment specifically. Important to look at this line. I know that some of you think that piezo is high voltage. These piezos are not, and the maximum voltage is 14 volt RMS and 11 volt RMS as shown in this table. So just to show you this payload, this one, how it's built internally. This is 29 millimeter. Here is one motor. Here is the other motor. So this motor is working on a ring that is doing the azimuth, and this motor is working here on a ring that is doing the payload. In the next slide, I will show the internal structure, and basically, Ronnie said we want by the end of this presentation to give you the tools to understand where and how to use our motor. So here, true, we designed the whole gimbal and we are selling the gimbal, but basically our technology is reflected in 3 types of parts that are here. First of all is the motor. You can see here 1, 2, 3, 4 motors in the azimuth. And yes, the motors are additive, and you put more motors, you get more torque. 2 motors on the tilt. The motors have to work against the yellow part. The yellow part is hard ceramic that we provide, and all our control, all our stabilization are embedded in a custom chip, which is 4 by 4 millimeter. So this is the gimbal, and this is where the piezo is, and we can scale it up and down. I decided not to put it in the presentation as basically I can tell you that the bigger gimbal has 8 motors on the azimuth and 4 on the tilt. I mentioned bandwidths, so I think it's worthwhile looking at body plot. And you can see here, if we look at the phase of 180, we are here. We go here. So we talk about a bandwidth of 200 hertz. This is the open loop. So pan is 200 hertz, tilt is 250 hertz. We have presented this data to several relevant customers. They were all very impressed. What we think from what we saw that basically conventional gimbals are about 4 times slower than this, which gives us the ability to do very fast control. And so here I'm showing the stabilization. Basically, this is what we put the payload on inclined in 45 degrees. You can see it here. Picture is not so clear, and we rotate it. And this way we stabilize in both axes. We chose to do it at night condition because at night condition, you cannot do software stabilization, because software stabilization will not overcome the smear inside the frame itself. Here you can see how sharp the images are. The same building at night. This is a camera at 9 hertz, but you can see, so that's why you saw this sluggish effect, but you can see the quality of the stabilization here as well. So small size, active stabilization, very good quality. Now, because this is an engineering forum, we also put this slide. This slide is showing that we are doing a perturbation of ±1 degree at 10 Hertz. This is the signals of the velocity and without stabilization, and this is with stabilization. So from ±1 degree, we get RMS of 70 microradian, which is, you know, just to say 70 microradian is not enough, because always you need to define the perturbation. So this is in a perturbation of ±1 degree, so the attenuation is around 500 to 1 at 10 Hertz. I think very impressive. So far I spoke about the size of the gimbal and the quality of the stabilization. I mentioned the very high torque, and the very high torque allows us to do this. So people that are involved in electro-optics know that in electro-optics in general, and in infrared specifically, we have the straw effect, like you are observing the world through a straw. So what we are doing is we are doing 8 field of view per second, move, settle, stabilize, move, settle, stabilize. This is the pictures, how we take them. And just, I want to, excuse me, I want to stop the video for a minute. Let me do it again. Okay, here you see, if you just look here, you don't know what you see. Very difficult. And when we doubled it 3 by 2, suddenly you get outstanding information. This is very important. We attended the conference in North Carolina on drones, and we saw how missions of search and rescue are conducted during daytime with the camera, with zoom, etc. At night, a thermal camera of 640 by 480 pixels, you are really blind and you cannot find the target. So this mosaic is a unique capability of our gimbals, and it is facilitated by the high torque, high acceleration. To throw a number on the acceleration, we are talking here about 90 radian per second squared. And it's written here 10, but I think more realistic, 8 frames per second to generate such a picture. And this is how this gimbal is looking when it's taking the picture. So stabilizing is one thing, but you have to understand that to do what we are showing here, the inertia is not working with you, is working against you. And therefore you need torque to do it, and you cannot do it in a miniature gimbal, and the piezo gives here a tremendous advantage. And last picture, you can see from what I'm showing that the scanning is configurable. We can do 2 by 2, we can do without, we can do 1 dimension. And this is, we have a GUI that can change it on the fly when the gimbal is on the drone. Now, we all know that the bandwidth of the channel between the eye and the brain is 0.5 megabit per second. So here we are talking of more. So basically, we are not able, if we want to look and capture an event, here we have a problem, limitation of our acquisition and processing. And therefore, when you go for larger matrices like this, it's important to combine it with analytics. So just, I will show the slide of analytics soon, but just to explain, if we are going to do, let's say, 640 by 480, we're talking quarter mega, 8 picture, we are talking about 2 megapixel per second. And this is achieved software configurable from a gimbal of 300 grams or 400 grams. And if we take the same logic with the camera of day camera of 12 megapixel, we are talking about around 80 megapixel mosaic per second. We all understand that there are cameras, infrared cameras of 2 megapixel, but they weigh a lot and they cost even more. So our solution is a 300 gimbal on a DJI matrice that can do it. And this is disruptive. Both sensors on the dual can do this matrix. And basically, we know that infrared is good for detection, visible is good for identification. There is complete registration between the two sensors on the drone, as you can see here. And this is some numbers on detection and DRI for those that are familiar. Detection, recognition, identification range. So this is the numbers for the EO camera for a human, basically detecting a human at 3.6 kilometers in the day camera and detecting a human at 1,000 meters with the thermal camera. Now about the analytics. So the human brain doesn't recognize well thermal images, first of all, and the other thing is limited, as I said, to 0.5 megapixel per second. For fast and efficient search mission, like there is a fire and there is somebody caught in it or accident, you need, it's beneficial to have data analytics. We are cooperating on that with a third party to provide this capability. So our job is to provide excellent stabilized panoramic image. We interface with third-party software which sits on our payload to do the analytics. And the analytics is done airborne. Why? Because the RF channel between the drone and the ground is limited. And we cannot push there so much information. So if we have the wisdom to check up on the drone what is the relevant images, we can select and send only the relevant information down to the ground station. So we can cover a lot of area with the numbers that I indicated before without suffering from the limitation of the RF channel. Here we see an example of very rudimentary analytics detecting a human, and we can do that at a kilometer. So I'm going, I just want to repeat what we covered so far. We covered miniaturization, we covered stabilization, we covered mosaic, and we covered analytics. I don't know, but those of you of the forum that are my age know this girl. Her name is Lena. Lena was the picture that was used when I was a student for image analysis algorithms. Many years after that, I found out that she was a centerfold of Playboy. And actually, I saw a picture of the whole body, but let's not elaborate on that. What we are demonstrating here is something also facilitated with our payload, which is to do super resolution. We know that there is the original image, and then there is geometric transformation because of the pixel, and there is optical blur because of the lens, and there is sampling problem, and there is noise. So basically what we acquire is much inferior to the original. And there is, we are not inventing this algorithm, we are just using it. There is an algorithm to do an approximation. I'll jump to this slide. Basically what we are doing, our gimbal can move very easily half a pixel. So this is basically the pixel. We move half a pixel to the left, half a pixel up, half a pixel to the right, half a pixel up, half a pixel left, half a pixel down. And then we have equations to estimate the image in higher resolution. Theoretically, if you do 2 by 2, you improve by factor of 2 the resolution. In reality, it's maybe square root of 2. And here I'm going to show you, we took this picture of a building. Here the resolution, you can't see, there is bicubic interpolation or super resolution. Super resolution is we are solving it. But now in the next slide, I'm going to zoom on these windows and you will see the effect. Here, this is the day camera. These are the windows that we saw. Look at the elliptical blue sign and see what happened when I applied the super resolution. We see that we were able to extract more information. Again, let's just understand. The pixel resolution is IFOV is around 100 microradian. To do that, you need to move 50 microradian. We can easily do that. As you saw, we can do 1 microradian. And we apply the algorithm and basically can improve the resolution. So this is another capability which is facilitated by the piezo. Okay, so far I spoke about the gimbals with the emphasis on UAVs. I want to say a few words about AGVs as well. AGV is autonomous ground vehicles. So we know that many groups are working on LiDARs. I'm not going to say anything negative about LiDAR. I know this technology for many years. I think I saw the first LiDAR in Israel, which was in Terra Santa in Jerusalem in actually it was 1976. But I think that LiDARs might have a problem for AGV. AGV is operating in confined area. Think about what, let's say, Amazon is doing in their warehouses. There are multiplicity of AGVs near human workers. And then I don't want to frighten anyone, but this is the eye safety maximum permitted exposure in different wavelengths. And we see that there is a limit. Above this limit is not good that the laser will hit the eye. So this is in the visible range or up to 1 micron 0.06, which is the neodymium YAG laser, or or this kind. And there is another, which is that in the longer infrared, around 1.6, also around 1.5, there is also laser. The issue of eye exposure in short distance with it is could be a problem. I'm not saying it is a problem. And I think also this is clear. There are two cars standing, and it's not AGVs, but for the sake of the demo. And this, the lady passing here is a Lambertian scatterer, which means scattering from this laser will go here, and the scattering from this laser will go here. And basically, each LiDAR could get a ghost image. So this one will see the lady here and the lady here, and this one will see the lady here and the lady here. So this could be a problem. Also, when you have a lot of units, this direct blinding could be a problem. So, you know, this is just general observation. I want to stress I'm not preaching against LiDARs, but excuse me, physics talks, and I see a problem. So, excuse me. So we came with a proposal. Before the proposal, another problem, especially for short distances, if you put the LiDAR here, there is an area of miss, which could be 3.5 meters. So let's say if this is moving, especially if this is moving slowly, like an AGV, and something is happening here, in this area, the LiDAR is blind to what is happening here. So this is going at a meter per second, and the blind area is 3.5 meter. We are talking about 3.5 seconds that something can happen, a child can go here, and the system will not detect it.
Nir, I'm sorry for interrupt, but we have a few more minutes. We have
I know.
waiting.
I'm confining to the time. I have 200 more slides only.
No problem.
No, finishing. So basically what we are proposing is the approach of parallax of two miniature gimbals. We actually thought also of a gimbal in the headlamp. And here we show what is the parallax effect. You know, this is the way we perceive depths. I will not go into the calculation, but let's say if the distance between the two gimbals is 1 meter, we get improved reading of distance, completely passive, no crosstalk, which improves according to the square of the distance. I mean, inversely proportional. So at 100 meters, we have 10%, or 5%. At 20 meters, we have 2% accuracy, which I think should be considered for sure. The gimbal itself could be a very small gimbal. This is even smaller than what I showed before. We put it on a helmet also. And this is the target gimbal, smaller than that. 1D scanning is enough because the opening is high. The wide vertical field of view will diminish blind spots. And we believe in it, and we are involved in a European initiative on using our payloads on AGVs, actually 2 European initiatives. Summary, Piezo has many advantages for payloads. The company is focusing on the commercial market. I miss an on here. Sorry, another error here. We welcome discussion of application for our Velocs, which is this gimbal, which we are launching, this one. So thank you very much.
Thank you, Nir.
Thank you, Nir. Yes, Tuvia, there is any question, please, we can go over the question. We have a few minutes.
I see how the motor react under harsh environment conditions. Question by Shlomo Nezer. I don't know what is harsh, but let's say temperature range from -45 to 80 degrees, we have a lot of experience. Vibration, we have units on airborne applications with the 14G RMS. We are launching units to space. We suffer in the launch also a few tenths of G. Our shuttles are mounted on a rifle like M4, suffer 1400 G pulse. So I would answer this question overall very robust. There are design considerations that are needed in do's and don'ts how to do this motor. You know, like the difference between driving a Volkswagen buggy and driving an Alfa Romeo. Usually I say Ferrari, but I don't want to sound arrogant. So obviously the Alfa Romeo can get much better performance, but you need to drive it correctly, you need to change gear in the right time, etc. This is also true for our piezo motor. So I hope I answered the question.
Tuvia, there is any more question?
No, currently no other open questions. But this lecture and the presentation will be uploaded to the website, and everyone can ask their questions in the time that they find appropriate.
Well, okay. First of all, thank you very much. Thank you, Dr. Karasikov, and also to Tuvia from Nanomotion Technologies. I think also we are on time on that. I think we saw here the added value of Nanomotion Technologies. In some cases, it enables disruptive enhancement to payloads capabilities, enable them new capabilities and much wider solution to the user. This is some parts that we saw here in like the cases that you shown about the mosaic and some others. And I believe that after getting to know the principle of the technology and to use this building block, we can first of all take it to many more cases, not only to that kind of payload, but to many more cases. And it can bring also it's some kind of technology that knowing that it's there, you can build around it many more solutions, just knowing that this building block is there. So I believe that the sky is the limit for this kind of building blocks. And I want to thank you very much for this really excellent presentation. And I hope that everybody enjoying. So thank you very much.
Thank you. It was a pleasure. And you said a lot of application, you know, I was limited in time, so I decided not to put it, but still I want to mention it. The issue of laser steering is where you need fast response and high accuracy is classical for our technology.
Thank you all.
Thank you very
Nir,
much. We will
thank you very much.
short
Bye-bye.
everything.
And Mickey, of course, thank you.
Thank you, Nir. Yeah, it was a great lecture. Thanks very much, and we'll be in touch.
Yes, appreciate this organization, guys. Bye.
Bye.